Okay, so in this lecture, we will continue learning more analyses. We have seen in previous lectures how to apply nodal analysis and mesh analysis. Today, we will continue with learning more analyses. So, at the beginning, we will learn the superposition and the source transformation also, and then the Thevenin and Norton's theorems in this chapter. So let's start first with the definition of the linearity. The linearity basically means that, and in our case here, we're dealing with the circuits using Ohm's law. We know that V equals to RI, which means that the relationship here between the voltage and the current is proportional to the resistor. As long as my resistance is constant, not changing, then I have a linear system. And in this case, if I look at my current versus voltage, then the relationship would be like this, ideally. Practically, this curve will reach a point where the loading, for example, of the thermal exceeds the limit, and that's why it becomes nonlinear, and then it may end up damaging the resistor. But in our course, what we care about are ideal resistors here, which are basically having constant value, which means constant slope, and the relationship between the voltage and the current is linear. It also requires that the response of the circuit to a sum of sources equals to the summation of the individual responses due to those sources, due to each source separately, one at a time. We will see what does this mean, but what we need to know that our circuits that those resistors are made of are linear circuits. So let's first look at the superposition technique. Superposition is another way to analyze circuit, and it uses a simplification that we will see in this lecture. So we have seen nodal analysis and mesh analysis. In case we have more than one independent source, things will start to get difficult to use Ohm's law by itself, and that's why we've learned how to do nodal analysis and mesh analysis. A third way is to use the superposition. And how does this happen? The superposition says or states that the voltage across or the current going through any resistor is the algebraic summation of those voltages or currents that this element is seeing due to each independent source acting alone, so one at a time. So if I have a circuit and that circuit has two independent sources, if I want to apply the superposition, what I need to do is I need to use one independent source at a time, which means I keep one on and I switch off the second one, and then so this means that I will look at the response due to one's independent source at a time and switch off the second one. If I have a circuit that has three independent sources, in this case, I will turn on one at a time, which means I'll turn on one and switch off two. This is only for independent sources. What about the dependent sources? We leave them intact. We don't do anything to them because they depend on a variable in the circuit, and this variable is going to be based on each independent source. So as I said, we are only dealing with independent sources in terms of switching them off and keeping one at a time. We don't touch the dependent sources. And then we, at the end, do algebraic summation to those responses to find the total value, either a voltage or a current. So how do we do it? Again, we turn off all independent sources except for one source. We calculate the voltage or the current due to the existing uh, dependent source and one independent source using any technique you want. You can use mesh, you can use nodal analyses. And then we repeat this for the remaining sources, independent sources. And then we find the total contribution by algebraically adding those results, either voltages or currents. So one, two things to keep in mind when it comes to switching off, and we will see this in an example. When I say switching off an independent source, this means that the result would be zero. A voltage source will be 0 volt, and a current source will be 0 ampere, right? This is the meaning of switching off, because a voltage source generates voltage, a current source generates current. So when I say a switched off voltage source, this means 0 volt. When I say switched off current source, this means 0 ampere. But the definition of 0 volt is a short circuit. And the definition of a 0 ampere, a zero current, is an open circuit. And we've seen that before. If you look at a piece of wire, for example, here the potential is going to be the same, and that's why, so this is 1, 2, so V1 and V2, for example, because I connected them with this piece of wire, so this is taken from a circuit, V1 equals to V2, and that's why the voltage across here, which is V1 minus V2, becomes 0. So that's why a piece of wire has a voltage drop of 0, because it belongs to the same electrical node. So the potential difference is 0, right? So when I say switched off voltage source, this means I am replacing it with a piece of wire. Now, when I say switched off current source, so here, let's assume I have this current source. When I switch this one off, this means I equals to 0, an open circuit, right? So whenever I have an open circuit, I have a 0 current. So that's why when I switch off independent sources, a voltage source, I will be replacing it with a piece of wire. And a current source, I will be replacing it with an open circuit, right? Dependent sources are left intact. So let's look at this example to understand how we apply the superposition. Example 1, use the superposition theorem to find V naught. So we need to find V naught. So when I say use the superposition theorem, this means I will need to keep one independent source at a time. So how many independent sources do I have here? I have 2 independent sources. The 5 ampere and the 12 volts, which means I will switch them off and keep one at a time. So switching off the 12 volt, the voltage source, 。 I will have to redraw the circuit now, right? Because I am doing some physical changes to my circuit. So if I am to switch off the 12 volt and keep the 5 ampere, the 12 volt is a voltage source. Switching it off, replacing it with a wire, so it becomes 0 volt. So in this case, if I am to redraw the circuit now, this is 2 ohm. And now I will call this one V naught 1. So V naught 1 means due to the circuit number 1, which basically having only the current source. So this is now a piece of wire. In this case, I can use the current division, right? I can use the current division in order to calculate the current in here. So let me call this one I1. What's I1? Why? Because I have now 5 and 5. Well, if you look at it by inspection, you should be able to know how much is the current, because I have a 5 ohm on the right side and I have a 5 ohm on the left side, which means that the 5 ampere is going to split into two equal currents. But just to show you, using the current source as a general case, I1 equals to 5. The other resistor, which is this 5 divided by 5 plus 3 plus 2, and I1 is 2.5 ampere. If I1 is 2.5 ampere, then V naught 1 is I1 times 2, and then V naught 1 is 2.5 times 2 is 5 volts.
Sure.
Yes.
So this equation I'm having trouble understanding. I1 is equal to 5 times 5 over 5 plus 3 plus 2. So that's 5 amps times the resistance
The
here.
ratio of the other resistor to the total resistance.
I see. So which one is the amperage? Which 5 value?
This one. This one is the ratio of resistance
Okay.
of the other branch to the total, to the summation of both branches. Okay? So this was for switching off the voltage source. Now switching off the current source. Replacing the current source with open circuit. So I have to redraw the circuit again. This is a unitless. That's a ratio. Resist ohm divided by ohm. This is ohm divided by ohm, right? That's the ratio of the resistance of the other branch divided by the summation of the resistances in both the branches. Now the circuit, when I switch off the 5 ampere, I will be replacing it with an open circuit. The voltage sources will be there. So here I have the 5, I have the 12, three, 2, and this one now will be V naught 2, because that's a new circuit, right? So in this case, I have a circuit that is in one loop. I have now 5, 3, and 2. All of them are in series, and they have one current. Let me call this one I2. Then what is this current? I2 is 12 divided by the summation of all resistances. So 5, 3, and 2. And I2 is 1.2 ampere, right? Then what is the voltage V naught? 2 is 1.2 times 2. Then V naught 2 is 2.4 volt. And now the total V naught, which is V naught 1 plus V naught 2, equals to 5 plus 2.4 is 7.4. Any question about this example? So this is, we have two independent sources. We switch them all except one, and we take them one at a time. So if we have three independent sources, we switch off two and keep one. If we have four independent sources, we switch off three and we keep one, and then we do it for each independent source. Any question? Yes, go ahead.
So when we rewrote the first time, we were looking for I1 coming out from a node, but in the second case, it's I2, which is around a whole loop.
Matthias, the circuit has completely changed.
Well, yes. So the I2 you're designating is current going through an entire loop in this rewritten circuit.
Absolutely, because all of them are in series now. That current source is gone. Now it's an open circuit. There is no current going into that open circuit. So all the current now is going to go through that loop. In this case, the resistors 5, 3, and 2 are in series, and they share the same current. So applying Ohm's law would be the total voltage divided by the total resistance, which is the summation of those resistances, 5, 3, and 2 equals 10, right? Is this clear?
Yes.
Okay. Any other questions before moving on to the next question? Now, the next question we have a dependent source as well. So let's see how we can deal with this question. So here we have two independent sources, and one dependent source. We need to use superposition to find Vx. Where is Vx? Vx is across this current source. right? Why? Because this is my reference. This is my reference. Okay, so in this case, I will start with switching off the voltage source. I will redraw the circuit. Again, switching off a voltage source, an independent voltage source, means that we replace it with a piece of wire. Redraw the circuit. So I have here 20 current source, wire 20. This one is VX1. 4 ohm. The dependent source here is 0.1 VX1, right? Now it's not VX, now it is VX1, so that's why I changed also the variable here to VX1. Now we need to find this VX1. So how do we find this VX1? So we have a current source here. If you apply, let's see if we do a KCL here, what do we get? We have this current and this current. Okay, or maybe we can do a nodal analysis. So let's do a nodal analysis. So what are the nodes that we have here? So let's put the reference here. I have a node here, and I have a node here. I can color them for you, if that's easier. See, all the wires connected together will make one node. So here, so I have two nodes. One of them will be dedicated to the reference. So I need to write only one nodal equation. So if I am to nodal equation 1, in this case, I would be saying Vx1 over 20, or if you want to say Vx1 minus 0, but right away Vx1 over 20, 5 ampere is entering, minus 5, plus Vx1 over 4. So this is a review for the nodal analysis as well, minus 0.1 Vx1 equals to 0, right? So make sure that you did not miss any of the branches. So you have 1 branch, 2, 3, and 4. 4 branches, right? So this is the nodal equation. What else you need now? You can solve now. You have one equation, one unknown. So if you multiply by 20, Vx1 minus 100 plus 5 Vx1 minus 2 Vx1 equals to 0. So Vx1, 5, 6 minus 2 is 4. So 4 Vx1 equals to 100. And Vx1 is 100 divided by 4. Vx1 is 25 volts. Right? So this is Vx1 due to the current source while switching off the voltage source. "25 volt is on, 5 ampere is off." I need to redraw the circuit here.
Sure.
Yes.
So the key here is Vx1 is 25 is only the voltage Vx, only when the voltage source of 25 volts is turned off.
And the 5 ampere is kept on.
Okay.
So remember, in superposition, you always need to keep one independent source on and switch off all the other independent sources. So this is V.1, now Vx2, right? Okay. Again, between here and here, Vx2. So we need to calculate this Vx2. What is the best way to calculate Vx2? You can use, if you want, mesh, or you can use nodal. If you use mesh, and let's do mesh analysis, that's going to be a nice review for all of them. I1, I2. Remember, we had here a current source, dependent current source. So I2 is minus 0.1 Vx2, right? Right away. What about I1? Let's write the mesh equation for I1. So mesh equation 1 minus 25 and I have plus the resistors that this I1 is going through is 20 plus 4 I1, right? Then I have minus 4 I2. equals to 0. Again, re-examine your circuit. You will see that your I1, your mesh current I1, is going through two resistors. You have two resistors here, the 20 and the 4. And that's why I added them, multiplied them by I1. I have I2 going in the opposite direction. Remember, both are clockwise, so this means any shared component, they will be in the opposite direction. So that's why I put minus for I2. And the voltage source is entering the negative. So this is my mesh equation. Now, if I take this I2 and substitute it here, now I need to come up with a relationship. So let me put I2 here. Substituting I2 minus 25, or I can take the 25 to the other side. So I have here 24 I1 minus 4. What is I2? I2 is minus 0.1 Vx2 equals to 25. I have Vx and I have I1. I need to come up with a relationship between this variable that is Vx2 from the dependent source in terms of my standard variables that are the mesh currents, right? We've seen that before. So I need to find the relationship between Vx2 and my I's, I1, I2. Let's see which one. I can see here that Vx2 is across the 4 ohm, right? Vx2 is across the 4 ohm. And the current in this 4 is due to both of them. So I can say here, and let me write this one in a different color. Here I can say, looking at Vx2 and the 4, where here is plus and here is minus. I1 is entering the plus, I2 is entering the minus. So Vx2 is 4 times I1 minus I2. This is the relationship that I came up with between my variable, that is Vx2 in this case, and my mesh current variables. Now I can take this one and substitute it here. Then I will be getting the following. 24 I1 plus 0.4 Vx2 is what? Is 4 I1 minus I2. Okay, so here, before I do this, let me pause for a second and continue this one with Vx here. So from here, I have Vx2 equals to 4 I1 minus I2, which is also minus 0.1 Vx2. Right? So let me add one more slide. Okay. So I have here Vx2 equals to 4 I1 plus 0.1 Vx2 or Vx2 plus 4I1 plus 0.4 Vx2. We take this to the other side, becomes Vx2 minus 0.4, 0.6 Vx2 equals to 4I1 or Vx2 equals to 4 divided by 0.6 on Vx2 4 divided by 0.6 is 6.667 I1. Now, if we take this and substitute it in the equation that we had earlier, which is 24. So we had the 24 I1 plus 0.4 Vx2 equals to 25. This is the equation we had earlier from the mesh equation. Now, if you take this Vx2, substitute it here, you will end up with one equation, one unknown. So this is going to be 24 I1 plus 0.4, 6.667 I1 equals to 25. Yes, go ahead.
Sir, I've found in the past that substitution with free variables is kind of tricky. So for something like this on a test, could we use a matrix instead?
You can use whatever you want. Yeah, absolutely.
Okay.
So we have here 24.4 times 6.667 2.67 I1 plus 25. So 24, 26.67 I1 equals to 25. Again, remember, I'm evaluating you in this course on your understanding to how to formulate a circuit into equations more than the calculations. The calculations, they do have a weight, but the most part I'm interested to see is how do you formulate those problems into equations divided by 26.67. So I1 is 0.94 ampere. Back to here. We found I1. We need to find I2. what is the relationship between I2 and I1. Okay, so we can find Vx2 right away from I1. So Vx2 is 6.667 times 0.94, and Vx2 is 6.25 volts. So Vx is Vx1 plus Vx2, and Vx1 was 25 plus 6.25. Vx is 31.25 volts. Okay. So this example basically summarizes all what we have learned so far. So this example is a very important example. Again, I'll let you deal with the math the way you want. You want to use the matrix, it's up to you. Okay. Regarding the office hour, yes, I'm still looking at the results here, and I thought I put I did put a deadline. Let me see here. Where are we in terms of the survey? I put the survey. How many students submitted their response? We'll see here. I'm gonna close it now and tell you when is the office hour. Okay, so we have here same number 5, 11 till 11:50. So 50%, 50% between 12 to 12:50. So it's gonna be either it will be either 11. If you have not casted your vote here in this survey, please do so ASAP, because we have a tie here between Fridays at 11 and Fridays at 12. So by the end of this lecture, or after the lecture, few minutes after the lecture, I will close this survey, and it will be either at 11 or at 12. So we do have an office hour tomorrow. It's going to be either 11 or 12. I'll let you know maybe an hour after the class. Okay, so this is how we solve the superposition. In this superposition example, we used nodal analysis, we used mesh analysis, because we had still a dependent source that really requires a kind of more advanced technique than just Ohm's law or Kirchhoff's laws. So this example is a very important example, covered all what we have learned so far. If you don't have any further question, we can move on to the next part of the lecture.
Sir, could you just go back to the last slide for like 1 minute?
Okay, sure. This one?
Yeah, that one. I just had to write something down.
Sure. I'm posting the lectures with PowerPoint format. So all what I have written here on those slides will be posted to you right after the lecture. Are you done?
Thank you.
You're welcome. Okay. Now let's move on to the source transformation. Source transformation is another technique that will allow us to transform sources from one form to another, like what we have seen in delta Y transformation. This technique can be useful in simplifying circuits as well. Now, in source transformation, you have to make sure that you are moving between those two shapes. In other words, if you have a voltage source that is connected this way with a resistor, such that they are in series, this shape can be transformed into a current source, and the resistor would be connected in parallel. So notice that the R did not change between the voltage source and the current source. So the condition is the voltage source has to have a resistor connected to it in series. Once you have a current source that has a resistor connected to it in series, this shape of a circuit or of a source can be transformed into a current source that has the same resistor but now connected in parallel, such that the arrow of the current source is going from the positive toward the negative. Notice this arrow maintains the same direction such that the arrow is from positive toward negative. And the same thing for converting or transforming a current source to a voltage source. You have to have this shape, a current source that has a resistance that is connected to it in parallel. In this case, you transform it such that this resistor stays the same. However, now it will be connected in series with the voltage source, and the voltage source Vs would be this way, such that the positive, that the current is going from positive to negative. Now, something to keep in mind, that the relationship here is Vs equals to RIs. So let's assume you have Is and you have R and this current source topology. You want to transform this one to a voltage source. So what you do is you calculate first Vs, and then you draw this circuit, and you put the plus minus this way, such that the arrow is going from the positive toward the negative. See, so the arrow like this, and the plus minus are like this for the voltage source. Now you have to keep in mind, you cannot do any transformation if this resistor is 0. You cannot do any transformation if this resistor is infinity or does not exist. In other words, if you have a voltage source in a circuit, right? Like this, for example. This voltage source has a 0 resistance connected in series to it, either here or here, doesn't matter. You cannot do source transformation. You cannot transform this one to a current source. On the other hand, if you have a current source and this current source does not have any resistance in parallel to it. Look at the resistance in parallel to it. It could be an infinity, right? Because there is nothing. We don't see anything, which means it's a very high resistance. It could be an infinity. Then you cannot transform this current source into a voltage source. You can transform this one from voltage source to a current source, right? This one can be transformed because it does have a resistance and series to it. So always keep this in mind. Same thing applies to the dependent sources as well. So no difference at all. You can transform dependent source from voltage dependent source to a current dependent source and vice versa. Exactly the same way. And the current are here in parallel. This R becomes in series when it goes to the voltage source. Okay. Now let's do a few examples about how to do source transformation. We have two examples here. We have an example for this circuit that is made of independent sources only. We need to do source transformation. The objective is to minimize those sources as much as possible. Simplify that circuit as much as possible. So here in this case, just looking at this circuit, I can see that I can do source transformation. Here, for example, I have this current source that has resistor. So the objective is to find I naught, right? So I naught, I don't need to touch this branch. I'm coming to this. So the branch that I'm asked to calculate the current that goes through, I should not be touching. Don't do any change to this, to just do this branch. You can do all the changes you want to the other circuit. So how do we do this? Okay, so let's look. I need to identify the following. Current source with resistors in parallel. This can be transformed to a voltage source. So if I take this resistor that is connected in parallel with this resistor, and I found the equivalent resistance that was still in parallel, I can then later on transform this current source with that resistor in parallel into a voltage source. So let's do this. Now the circuit is going to look like the following. Again, I don't need to do any changes on this 7 ohm because it has the current that I want to calculate. Any changes in it will change the whole value. And also I have this current source. So this resistor, let me call R1, is indeed the contribution of those two. So those two are in parallel. So 6 times 3 divided by 6 plus 3. 6 and 3 will always give you 2. So keep this in mind. So R1 here is 2 ohm. So this one is 2. This one is 4 and 1 are in series, right? So the result here is 5 ohm. And let me call this one R2. It's 5 ohm. Now, what can I do with this? This is a current source that has a resistor in parallel, R1. Now this will be transformed into a voltage source that has the resistance R1 in series. So this one will be
Papa, are you on the meeting?
okay. So now we need to calculate this voltage source. It's 5 times 2, right? So here is 5 5 times 2 equals to 10 volts. So this is 10 volts. This is the circuit due to the transformation of this 5 ampere. Now this circuit can be now simplified further. I have the 5 volt and the 10 volt sources are connected in series, right? So this is going to result into the summation of those two. So I can now redraw the circuit to look like the following. Five plus 10 this is 15 volt, right? 7, then 3 ampere, and 5 ohm, right? Now look what I'm going to do. After I did this, after I combine this voltage source, the 5 with the 10, and now I have a 15 volt. Now I will retransform this 2 ohm and the 15 volt into the current source. So in this case, those two, I'm bringing them back to current source. In this case, What is the current? 15 divided by 2 equal 7.5 ampere. Is that right? Okay. Now I have 7.5, 2, 3, and 5. So let me redraw now the circuit. Doesn't matter swapping, right? They're in parallel, 3 and 5. So we have 5 here. And this one that we don't want to touch. Now this is my circuit. What I can do here, I can combine this 5 and 2, and also I have the 3 and the 7.5 ampere also are connected here in parallel, so they are going to contribute the current. So what you can do is, if you combine those 2 and 5, that's going to be R3 2 times 5 over 2 plus 5 R3 10 1.42 43 ohm, and the 3 and the 7.5 are also connected in parallel. As you can see here, they are going to result into a current source. So I have here IS equals to 7.5 plus 3. So IS is 10.5 ampere, right? How did we come up with this? I'll show you. Now, if I am to simplify this further, so it's going to look like this. Now remember, all those are in parallel. What does this mean? This means I can swap their locations just to make it simpler to you. R3 1.43, and then I have 3 ampere, and I have 7.5 ampere, right? Now notice that if you do a KCL, just to understand, and assume that you have a current here, call it whatever you want to call it I1. If you do a KCL here, you will notice that those 3 ampere and 7.5 ampere are going to add, right? So it will be an equivalent. Take a KCL. If you take a KCL minus a 3, so here, say KCL, call this one A, at A. So you have 7.5 entering minus 7.5. You have 3 entering minus 3. You have I1 leaving. You have I naught leaving equals to 0. What does this mean? Look at the 7.3 and 7.5 and the 3. They are adding. So the result here is minus 10.5 plus I1 plus I equals to 0. So this one is what we have done here, right? So now this one can be represented by one current source that is 10.5 ampere. And this one is my 1.43, and this one is my 7 that has the I naught. Yes, go ahead.
Is that IS you wrote there?
Yes, this is, I'm calling IS, which is the total
Okay.
current.
Okay.
Okay. Now, what is I naught? Using the current division, I naught would be 10.5. Can somebody tell me what is the ratio here for the I naught for using the current division? What is the I naught using current division? What shall I put here in the numerator? What shall I put in the denominator? I need I naught. What shall I put? No, I naught is not equal to IS. IS is going to split into two currents. One goes here and one goes to I naught. What is I naught using the current division? The resistance of the other branch divided by the summation of the resistances of both the branches. So it would be 1.43 divided by 1.43 plus 7, and I naught equals to times 10.5 as 1.78 ampere. Okay. Any question about how did we do the source transformation?
Actually, sir, I had a quick question about
Sure.
the division equation there. So when you're trying to find the current I naught going through the 7 ohm branch, you take, so the equation is the resistance of the other resistors connected to the node divided by all the resistances, the sum of the resistances.
Right.
So
So
if there was a third one,
no third one, no third one. We have to make them into two branches. This is the current division.
right?
Only
Okay.
applies on two branches of resistances.
So if we were looking for the current going through the 1.43 ohm branch, then we would have 7 as the numerator, right?
Absolutely.
Okay. All right. I see now. Thank you.
You're welcome. Any other questions? We only have 2 minutes left. There is one more example that I prepared for you, and probably it makes sense that you go ahead and try solving it. This example, but don't look at the solution. This is an example from the textbook. So the solution is in the textbook. It is solved. Don't look at the solution in the textbook. Try to do it yourself first before you look at the solution in the textbook. In today's lecture, we covered almost everything we have seen so far in the course, from all analyses or laws or everything. We covered it today. So today is an excellent lecture for you to go through again and practice and solve this question before looking at the solution. This would tell you what is the level of your knowledge so far in this course. And again, this course requires practice. So practice, solve questions in order to build the expertise that you need for the quizzes and the midterm. Now, the first quiz is on June 17th. So that's going to be Thursday, 11:30 a.m. So I will finalize the material later on, but I want you first to be aware of that date and prepare. Probably. Yeah. Have a good weekend. Thank you so much. Again, try solving this question. And if you have any question about the solution, we can discuss it later on. Have a good day. Bye.